Okay, we will start with question number 19 from the assignment. If we plug in infinity, which I use as a loose way of saying things, we can't really plug in infinity because it's not a number. But if I think about plugging in a huge number here, the ln of huge is huge, and the log of huge is huge. So I have infinity over infinity, which is where we can use L'Hopital's rule. So for L'Hopital's rule, then we're going to take the derivative of the top. The derivative of ln is 1 over. We need a chain rule, but it would just be times 1. Then on the bottom, we need the derivative of log base 2, or the general form, log base a. And what is the derivative of log base a?
ln of
x
over
x.
X
ln of a.
1 over x ln of base. So the derivative of ln is 1 over. Okay, log is just a different form of ln. It just has a different base, and the way we account for that different base then is by taking the ln of that base as well. Okay, 1 over x ln of a. The base of ln is e.
Okay.
So this formula would work even for an ln, because then we would have 1 over x ln of e, and the ln of e is just 1. So then that formula would still work in general for any log. When we divide fractions, that's the same as multiplying by the reciprocal. So this thing turns into x ln of 2 over x plus 1. If I plug in infinity now, or think about plugging in huge number times a constant is going to be a huge number. And huge number plus 1 is going to be a huge number. And I still have infinity over infinity. So then we can do L'Hopital's again. On the top, I do not need a product rule because ln of 2 is a constant. So I have a constant times x, and the derivative of that is just the constant. And on the bottom, the derivative of x plus 1 is 1. So this is the ln of 2.
So you just keep taking derivatives until
You keep taking L'Hopital's rule until you get a determinate answer. You can keep doing it as long as it is indeterminate. As soon as it becomes an answer, you need to make sure you stop.
I have a quick question.
Yes.
So let's say we have, I don't know, sorry, but if we have x goes towards infinity, theoretically, since we can't plug in a number for infinity, we plug in a really large number. Does that mean that if our final thing was x over x, does that mean 1, even though it's one infinity can be bigger than another infinity?
Yes, because x over x is 1.
Okay.
So, like algebraically, we can simplify it before we evaluate the limit.
All right.
For this one, our limit is heading towards 0 from the right. It's important that it's going towards the right because ln only exists on the right-hand side of 0, so we can't really talk about the left-hand side of 0 for an ln. But otherwise, we don't really need to think about that too much in terms of our evaluation. If I plug in 0 or something very close to 0, I get 0, and the ln of 0, if we think about the graph of ln, the graph of ln looks like this. So as I head towards 0, I'm heading down to a negative infinity. So I have 0 times negative infinity, and that was one of our indeterminate forms. We cannot do L'Hopital's rule on a product. We have to do L'Hopital's rule on a quotient. So to rewrite this, I'm going to say this is the ln of x over 1 over x. Instead of multiplying by x, I'm going to divide by the reciprocal. Okay. Usually we do this kind of the other way and try to clean up something that looks like that and get it back to what the original problem looks like. But in this case, to turn it into a fraction, we're going to kind of like messy it up. Because now it's a fraction, and now we can do L'Hopital's rule. Because if I plug in 0 on the top, the ln of 0 is an infinity, and 1 divided by 0 is an infinity, so we have infinity over infinity. Okay. So L'Hopital's rule then, on the top, the derivative of ln of x is 1 over x And the derivative of 1 over x is going to be a negative 1 over x squared. I think about that as being x to the negative 1. So then that gives me a fraction divided by a fraction. So we can multiply by the reciprocal. And I'm going to end up with negative x squared over x, or negative x. And if x is becoming 0, we get 0. So in this case, our first indeterminate was 0 times infinity, and we got 0. Then we reworked it, and we got an indeterminate of infinity over infinity, and that's 0 in this case. Um, 27.
Okay, sorry. What does that limit mean though?
That means if we would graph x ln of x, whatever that graph looks like, as we approach towards 0 coming in from the right-hand side, the function is approaching a value of 0.
So the y value.
The y value is approaching 0. '27 says the limit as x goes to 0, again from the right-hand side, of the ln of x minus the ln of the sine of x. Okay, for this one, if I plug in 0, the ln of 0 is infinity, negative infinity really, but the sine of 0 is 0, and the ln of 0 is infinity again. So we get infinity minus infinity, and that's indeterminate because they might not actually be the same size. So we can't just say that infinity minus infinity is 0. We can't do L'Hopital's rule on a difference. We have to do it on a quotient. So we have to turn this into a fraction somehow. The way we're going to turn this into a fraction is by applying log properties. So back in Algebra 2, and again in pre-calc, we talked about logs and ways to combine them, or we use the word condense them. So if I want to put together 2 logs that are being subtracted into 1 log,
Same thing as dividing.
it's the same as dividing their insides. So this is the log of x divided by the sine of x.
That's
What is the
tricky.
theorem for that?
Log properties are related to exponent properties. So we can think about, as a side note, kind of how exponents work. If I have a fraction of like x to the 8 over x to the 3rd, that's x to the 8 minus 3, or x to the 5th. Logs work backwards of that. So if I have a subtraction, I can turn those into a division within a log. Okay. Now if I plug in 0, I have a 0 over sine of 0, which is 0, 0 over 0, and I'm trying to take the ln of something that I don't even know what it is. So that's a problem. So in this, it's really the x over sine of x that's indeterminate. So we're just going to let the ln hang out. We don't need to do anything with the ln at this point. We just need to figure out what's going on inside of the ln, and then we'll take the ln of it. So we're going to do L'Hopital's rule on that x over sine of x, which would give 1 over cosine of x. Cosine of 0 is 1, so we get then the ln of 1, which is 0. So in this case, infinity minus infinity is 0, and the 2 infinities were actually exactly the same. But that is not always the case. In fact, it is rarely the case.
There's an infinite number of possibilities. Just, yeah, one of them.
Right.
So
29. Our next problem is an exponent one. We only got to one example of this in the notes.
yeah.
So if we plug in 0, e to the 0 is
1.
1 plus 0 is 1. And up in that exponent, 1 over 0 is
Undefined.
undefined or infinity. So we have 1 to the infinity, which was one of our indeterminate forms.
Which equals infinity.
it feels like 1 to the infinity should be 1, because it doesn't matter how many times you multiply 1 by itself. It seems like it should just always be 1. This is one of the ones that I think is the hardest to buy, that it doesn't work, but it doesn't. So I guarantee you if this is a multiple choice question, 1 would be an answer, because it feels like you just plug it in, you get 1 to infinity, 1 times 1 times 1 times 1, no matter how many times it seems like it should be 1. We said that when we have an exponent form, we're going to set that equal to L, where L is our answer, just standing for limit. You can use whatever letter you want. You can use Y, it doesn't really matter. I'm just saying this equal to my answer, and I don't know what my answer is yet. Now that it's an equation, I can do whatever I want as long as I do it to both sides of the equation, and so I'm going to take the ln of both sides of the equation. And I do that because it is a property of logs that then we can drop exponents down as multipliers.
Do you recommend doing this for every problem that has E in it? Like every
Not if it has an E in it, but if it's one of the exponential indeterminate forms. So 1 to the infinity, because the indeterminate was an exponent and not like a subtraction or division. Because L'Hopital's rule needs a fraction. And we can't apply it until we have a fraction, and this is the way we create our fraction. Right now it's not written as a fraction, but 1 over x times something is the same thing as dividing by x. So I'll just write it as a fraction then. As a side note, I am an extremely lazy person, I know I've mentioned before, and it is tempting for me to not write that ln of L over on the other side throughout the problem, but I find that if I don't do that, then I get to the end of the problem and I just box in whatever my answer is, and I forget that I need to undo that ln that I did in the beginning. So, I mean, you can kind of decide whether you think that's going to be a problem for you or not. But I know I have a tendency to, as soon as I get to an answer, I put a box around it and call it my answer. But it's not really actually going to be our answer here yet, so that's why I get in the habit of just writing that every single time, even though it is kind of annoying. If I plug in 0 now, e to the 0 is 1, that's 0 is 1, ln of 1 is 0 over 0. So we can now apply L'Hopital's rule. Remember, doing algebra to the problem should not fix the indeterminate. It should still be indeterminate, it's just a different indeterminate than it used to be, but it shouldn't actually fix the problem yet. The only thing that should fix the problem is doing L'Hopital's rule. So now the derivative of the top, derivative of ln is 1 over stuff, chain rule, times the derivative of stuff. Don't forget about your chain rule. So since it wasn't just ln of x, it was ln of lots of stuff, we need to multiply by the derivative of all that stuff. Divided by the derivative of x, which is 1.
Do we have to take derivatives of both sides?
No, because we're not really taking, yes. Yes. Okay. If we were actually taking the derivative of one side, then we would need to take the derivative of both sides. But we're not taking the derivative of this side of the equation. We're applying L'Hopital's theorem to it, which says take the derivative of the top and the derivative of the bottom. If we're actually taking the derivative over here, we would need a quotient rule, which is not what we're doing.
I'm going to assume that makes sense for the sake of time.
So a derivative on this problem would need a quotient rule.
Yes.
Low D high minus high D low, low low. And that's not what we did.
Okay.
We applied a theorem to it.
Okay.
Okay? And that theorem says that what's written here in this third line is exactly equivalent to what's written in the fourth line. So we didn't take a derivative. We applied a theorem that gives us something that's exactly equivalent. So since we didn't really truly change the left-hand side, we don't need to change the right-hand side.
Okay. That
We
makes
didn't
sense.
take a derivative. A derivative would have been a quotient rule.
I get it. It's just.
Yeah.
My mind.
Also, what are the rules for taking the derivative of the e to the something again?
A derivative of e to the something is e to the something. And then possibly a chain rule.
So e to the X
Derivative of
is
e to the x is e to the x.
How
Like,
e
what
to the
would
3x
e to
is
the
3 e to the
negative? What would like e to the negative 2x be?
Then you just need a chain rule. So it'd be e to the negative 2x times negative 2.
Oh, okay.
If I plug in 0 now, I've got 1 over 1 plus 0 times 1 plus 1, which gives me 2. And that is the ln of my answer. So to undo the ln, we use a base of e, so e squared is our answer. On to multiple choice, I can bet 3 of the answers would be 1, because that's what it felt like it should be right off the bat. 2, because people are going to forget to undo that ln, and then e squared. I have no idea what they would pick for the other 2 answers. Other common mistakes throughout there, probably like indeterminate or something like that would be an answer. And then I don't know about the other one, but I can pretty much guarantee those other wrong answers would be there because those are the really common mistakes.
Something like forgetting a chain.
Yeah. $33 is another one of the exponent ones.
I like number 31.
So 33, if I plug in infinity, ln of infinity is infinity. 1 over infinity is 0, so we get infinity to the 0. Since this is an exponent indeterminate, we're going to set it equal to L and take our ln of both sides. When I dropped that power down, it really did kind of create a fraction for us here. I just didn't write it that way, so now I'll write it as a fraction.
Is it always 1 over x? It'd be like x is x towards infinity.
The exponent could be anything.
Okay.
If this were a base box or whatever, would if we didn't write the limit as x approaches infinity, would we get marked down?
I'm not sure. I'm not sure. I do it just to be safe. Again, it's like I'm lazy and I don't want to do it, but it's not really correct math to stop writing it.
Okay.
So I do it just to be safe. I don't really know whether they would mark you down for that or not. At this point, if I plug in infinity, ln of infinity is infinity, and ln of infinity is infinity over infinity.
Why wouldn't you have ln of x on the second one? Why wouldn't you have 1 over x ln of x to the negative 1 because that's 0.
What I did from the first step to the second step was take this power and drop it down.
You can always do that.
That's the property of logs that we're applying. That's why we're taking an ln of both sides, is because that's a property of logs, that exponents can drop down as multipliers.
Okay.
So now we can apply L'Hopital's rule. So on the top, the derivative of ln is 1 over stuff, but that stuff needs a derivative as well, and the derivative of ln of x is 1 over x. Over 1.
So
Now if I plug in infinity, I get 1 over infinity times 1 over infinity. 1 over infinity is 0 times 0 is another 0. So 0 is the ln of my answer, which means my answer is 1. U is 0, which is 1. $35 is another exponential one.
Yeah, they were really good at splitting it half and half as exponential, non-exponential. Oh, I can measure this one.
If I plug in 1, I get 1 minus 2 plus 1, or 0, to the 0. This one is the easiest for me to buy that it's indeterminate, because I know like 0 to the 4th is 0, but 4 to the 0 is 1. A number to a number is a number, so then this is the easiest one for me to believe that it's actually indeterminate, as opposed to, like I said before, 1 to the infinity just really feels like it should be 1. So we use the same strategy no matter what type of exponential indeterminate it is. Set it equal to our answer and take the ln of both sides, which allows us to drop down that exponent. When I drop that down, this is not a fraction. And I need a fraction to be able to do L'Hopital's. So I'm going to rewrite this as the messier part divided by the reciprocal of the cleaner part. It technically doesn't matter which one you do. I just like, if I have to make something into a fraction, I'd rather make my cleaner part into a fraction than having like a really messy fraction on the bottom. It technically doesn't matter which one you do.
Could you divide it both sides by x minus 1, so then it's just x minus 1 on the bottom?
No. Because if I divide both sides by x minus 1, then on the left-hand side I wouldn't have a fraction, and so I couldn't do L'Hopital's rule. Because it would just cancel that other x minus 1.
Oh, right.
So it wouldn't really be a fraction. So then now I can do L'Hopital's rule. So the derivative of the top is an ln, so it's going to be a 1 over all the stuff times the derivative of all the stuff. So we need a chain rule up there. On the bottom, to take the derivative of this, I'm going to think about this as being x minus 1 to the negative 1. Okay. That way I get to avoid my quotient rule, otherwise I would need a quotient rule down there. So since it's just a 1 on top, I'm going to write it with a negative exponent. So then my derivative is going to be negative x minus 1 to the negative 2. Okay, this thing is hideous. So need to do some cleaning here. I'm going to factor out a 2 from that just to see if that helps me anywhere along the line. And the bottom actually also factors as x minus 1 times x minus 1.
Well, that's nice.
Okay.
Then on the bottom, this is going to be a 1 or negative 1 over x minus 1 squared. So then when I flip that thing up to the top and multiply by the reciprocal of it, I end up with some good canceling. So that cancels and that cancels. And then if I plug in a 1 now, 1 minus 1 is 0, times 2 is 0, divided by negative 1 is 0, and this whole thing turns out to be 0, which is the ln of our answer. So our answer is 1.
I like that. I like
keep forgetting that log is always basic.
That was 35?
That one is always basic.
Which is really not good.
That's important
Getting
to remember.
that.
41 is one more exponential problem. Clearly that was the biggest issue.
Yeah, we should have gotten more examples.
Ah, then we should have maybe talked less.
I want to make a statement this side.
Are you aiming that at
Never
me?
mind.
I'm aiming that at the general population. To anyone whose heart feels tugged when I say that. When I plug in a 1, I get, up in the exponent, 1 minus 1, 0. 1 over 0 is infinity, so I get 1 to the infinity here. This is the one that's the hardest to believe, but it is indeterminate. So I'm going to set that equal to L. Take the ln of both sides, which allows us to drop down that exponent. When I drop that down, I didn't write it as a fraction, but it really can be a fraction. I'm just putting the ln over the 1 minus x. And take the derivative of the top and the derivative of the bottom. And plug in 1 again. And get negative 1 is the ln of my answer. So my answer is e to the negative 1, or 1 over e would probably be the multiple choice answer. So here, I mean, by doing the problem, we can see that 1 to the infinity isn't just always 1. It turned out to be 1 over e this time. 52. 52 gives us the function 1 minus cosine x over x plus x squared. And asks you to first use graphs or tables to estimate what we think the limit is as x goes to 0. So we could graph that on in our calculator and say, what does it look like the y value is when x is 0? We could look at tables and see what does the table get pretty close to there if we're doing a small amount of change in our table. And then part B says, find the error in the following incorrect application of L'Hopital's rule. Okay, so first we have to say, is it even legal to do L'Hopital's rule on this problem? Because again, yesterday I said once students learn L'Hopital's rule and you start to get comfortable with it, every time a student sees a limit, they want to do L'Hopital's rule. But we can't do it unless we actually have an indeterminate. So you always, as your first strategy, plug in the number. So cosine of 0 is 1, 1 minus 1 is 0 over 0, and we can do L'Hopital's rule. So then in the book, their first step of the work says limit as x goes to 0, sine of x over 1 plus 2x. Have they made any mistakes so far?
No.
No.
No. Okay. So then their next step of the work says that this is equal to the limit as x goes to 0, cosine of x over 2. Have they made any mistakes now?
Well, yeah.
That is right. I
I
believe.
mean,
I
no,
hear that this looks right, but then I heard they made a mistake.
they did make a mistake.
What mistake did they make?
They can end at sine x over 1 plus 2x.
They should not have done another L'Hopital's rule. Because if I plug 0 into that previous step, sine of 0 is 0, but over 1 plus 0, that's determinate. 0 over 1 is 0, and they should not have applied L'Hopital's rule another time. So if you continue to do L'Hopital's rule past your answer, you will get a wrong answer, because then they at this point said, okay, now if I plug in 0, I get 1/2. Okay, which is not the right answer, but again, would probably be a multiple choice answer.
Could you do it again?
That's just
And then get it over 0 and be forced to do
If you did it again, then yeah, you'd get negatives. No, you'd get negative sine of x over 0, which would be 0 over 0, and you're back to an indeterminate.
Yeah, then you
And
take L'Hopital's rule
You
again.
can't though, because you can't take the derivative of 0. I mean, you can, I guess it's 0, but you can't really. So, I mean, you definitely need to stop when you're supposed to stop.
disheartening.
L'Hopital's is like a
Mistakes.
All right, we had a lot of questions on the homework, which is expected. L'Hopital's rule is tricky. We also had to rush through a couple of examples. So we're going to spend one more night doing some L'Hopital stuff. These questions are your homework questions. You have about 10 minutes in class to start working on them. But these questions we will talk about tomorrow as homework.
24 is kind of